It says 11:30 by my clock, so we're gonna get rolling. And I think they intentionally keep the temperature cold to keep the speaker and the attendees awake. It's like, damn, it's cold. And this is not San Jose. I live here for a number of years, but this is definitely not San Jose. All right, so this is not a Docker 101 session. I don't intend to teach you Docker images, containers, and stuff like that. We're gonna right away deep dive into the orchestration frameworks. How do you pick between either Docker as an orchestration framework or Kubernetes as an orchestration framework? What do? I do a bunch of things. I'm a Docker captain. There are about 70 of us around the world, which are recognized by Docker Inc. I am also a Java champion. I've been talking about Java for a number of years at Sun, Oracle, Red Hat, all over the place. I'm also a NetBeans Dream Team member. That continues to be my favorite ID. There are several other NetBeans Dream Team members here. That's kind of cool. Lifelong learner. I think that's sort of that's the thing that I enjoy the most. I'm always looking to learn and pick a new technology. And something that I'm extremely passionate about, if you were in the keynote, is about DevOps for kids, on how we need to fire up our next generation and get them ready. So let's jump straight to the meat. What does a typical Docker workflow look like? You got a bunch of images floating around. You want to run an application. Our application typically has multiple components. An application server, a messaging server, a caching server, a web server. Each of those, if you think about Docker container, it does only one thing, and it does one thing well. So in terms of how your application would look like, is your application essentially would be a lot of Docker containers collaborating with each other. But if you break it down further to a container level, end of the day, your client, which is on the left side here, makes a call to Docker host. In this case, I'm showing a single Docker host. But the client says, I want to run a container. The host says, OK, I'm going to run the container, but I don't have the image. So then the host goes and downloads the image from a registry. By default, it's Docker Hub, which is hub.docker.com. It's a SaaS hosted by Docker, where anybody can push an image. And once the image is downloaded on the host, then the container is started on the host as well. What's the role of the orchestration in this case? Well, one of the fundamental flaws of this flow itself is a single host, the single point of failure. So that means if your messaging server, web server, all of the containers are running on that host, and if that host goes down, your application goes down. It's not going to work for you. So typically, when you do a production deployment, you have a number of hosts running. And that's where the orchestration or the scheduler frameworks come in. OK, I'm going to take a look at the containers. I'm going to distribute them across multiple hosts. How I'm going to distribute them, how I'm going to make them talk to each other, what are the values that I'm going to provide so that your applications can talk to each other is what the fun is all about when you're dealing with scheduler frameworks or orchestration frameworks. So let's take a look at orchestration frameworks. What are some of the key things when I'm building applications using any of these containers? What am I looking at it? Nothing of this is new as such. It's just that I'm talking a little bit more in the orchestration language. From a developer perspective, I am trying to understand what are the core concepts that are available to me? What are my core abstraction layers? Can I create a cluster? Can I have a multi-node cluster? How do I deploy a single container? How do I deploy a multi-container application, which is typically the norm when you're building an application with containers? Now, when I'm building a multi-container application, then these containers essentially need to talk to each other. And containers are ephemeral. What that means is if a container dies, and if it starts up on a different host, it may be given a different IP address. Can I really rely upon the IP address of the container? So how does my service discovery and load balancing really work? So that's one of the aspects we'll talk about it. Now, most of the time, my containers are stateless. So if I'm running a Wildfly application server or a Tomcat or a Spring Boot, if it dies, I spin up another one. But if I'm running a database, that's a stateful container. So how does my volumes, where do I store the state of the container in that case? And first and foremost, before I even start, what is my local development environment? So what I'm going to do is I'm going to compare each of these aspects for both Docker and Kubernetes. And then you go a little bit on the ops side of it. Then you're looking at it, is my cluster only a single master cluster? Because essentially, master is the one that is telling where to schedule your containers in the cluster. How can I influence the scheduler? Is it only a default scheduler, or can I somehow influence the scheduler, schedule this container on a host that has X amount of memory or such and such SSD attached to it? Can I influence it in some such and such way? So rules and constraints and scheduler kind of go hand in hand in that sense. What are my monitoring capabilities on these different frameworks? Similarly, rolling update. And last but not the least, sure, you can roll your own solution, but end of the day, you want one throat to choke. You want to point finger at somebody. Hey, my system went down, so you go fix it. You be responsible for it. Sort of the commercial or cloud angle for it. Where can I run this on a commercial scale? So those are different aspects. We'll see how much time we got. And by all means, feel free to keep it interactive. I can talk about just this topic for 3 hours, and I'll try to condense it, but I want to make it valuable for you. You gave me your time, so I want to make sure that you feel valued here. Let's jump. So first thing first, let's take a look at the Docker core concepts. People often confuse when they talk about container, they talk about Docker. When they talk about Docker, they talk about container. I mean, vice versa. Realize there's a company called as Docker Inc., and then there is a container format called as Docker. When you're using Kubernetes or DCOS or ECS, any of those orchestration framework, they use the Docker container. And then Docker, the company, also has an orchestration framework, which is now baked into the Docker latest release. Like since 1.12, it is baked into the Docker runtime itself. So if you have Docker on your machine, 1.12 onwards, then you can say it's an optional feature, but you can say I want to run it in a swarm mode. And what that means is now I want to enable clustering support over here. What that means is I can run a multi-node Docker very easily. And the command for that is Docker Swarm init. And if your computer has multiple network interfaces, you say this is the host or this is the address where I'm going to listen at. Okay? So by default, the very first node in the cluster is a manager. Because essentially you're saying, okay, now I'm going to deploy my application. I'm going to give my command to the manager, and the manager can deploy it. By default, the manager is also a worker. That means if you're running a container, the application can run on that single manager. So it's a manager/worker, essentially. All right. The manager has two kinds of tokens. It has a manager token and a worker token. And you can get those tokens from the manager. And then when a new node comes up, you can say this node is joining the cluster as a manager or a worker. So you can easily have a multi-node manager or multiple or bigger cluster with one manager and multiple clusters. And we'll talk about sort of how we lay out our managers, number of managers, how do we decide, and all that stuff. You can just keep specifying the tokens, and your nodes will keep joining the cluster. So what I got here is I have a 1 manager and a 5 worker. So total a 6-node cluster, essentially, that I've created here. Okay. I can easily create a multi-node, multi-master cluster as well. So in this case, I'm saying Docker Swarm join, and I'm saying, okay, this is the manager that you need to join, and here is a manager token. That means you're joining as a manager, and then you're giving the manager token, because that's sort of the authentication mechanism with between the node and the manager. And then, of course, you give your listen address and IP addresses and stuff like that. So this essentially creates a multi-master Docker host cluster for you. Now, the request, when you are making a request to deploy an application, could go to primary or secondary. If it goes to secondary, it is automatically proxied to the primary one. And the primary is the one that is responsible for scheduling your containers on the host or on the different nodes of the cluster. Some of the key concepts, again, once the cluster is set up, essentially, all the masters are configured using a Raft consensus group. And so it's highly recommended that the number of managers in your cluster be odd numbers so that you can deal with the split brain problem of a network. So if in case the network splits, at least majority of the nodes are in one part of the network, and then they can make a decision on that. And similarly, on the bottom, what you see is all the workers. And those workers really communicate to each other using gossip network. The key idea here is your request, there is always a trade-off that you need to make. How many managers you want to have. So typically the recommendation is 1, 3, or 5, depending upon how critical your network is or cluster is. But the more the number of managers, that means the more they need to talk to each other. So, and then accordingly, they need to coordinate with each other on where a particular container needs to be deployed. So Raft consensus protocol is a very nicely defined, very algorithmic, very rather academic paper that is defined exactly what is happening in the Raft protocol. So I would recommend reading that. But from a user perspective, essentially, what happens is you say, I'm going to deploy an application. Whether it goes, it goes to anybody in the manager group. If it goes to primary, it gets delegated to, well, it goes to secondary, it goes automatically to the primary, and then the primary is the one then that's delegating it across all the workers. Other part also to note is you can also configure the manager to be pure manager, that, I'm purely for administrative purpose, don't deploy any containers on me, deploy containers only on the worker. So that's sort of some of the basic concepts you want to understand around when you're using the swarm mode as part of Docker. And this is 112 onwards. All right, I got a multi-node cluster set up now, and I want to fire up a service. I just want to run a simple Wildfly application server over there. So the commands, one of the big changes that happened in 113 is how the Docker CLI was restructured. So the commands are very intuitive. You want to create a service, you say Docker, which is your CLI essentially. You say Docker service create. Bingo, okay? And I want 3 replicas of the service. So you say -- replicas 3. Then you give the service a name, and then you give the image name, which is your Docker image. Now, in this case, when I say jboss/wildfly, that's coming from Docker Hub. I could have very easily pulled that image from a private repo, or from a repo which is inside the firewall, or whatever means you want to get the image from. So the point being, creating a service is as simple as this. And this is a declarative service. What I mean by that is, when you give the command Docker service create 3 replicas, it'll make sure there are 3 replicas running at a given point of time. So if a particular instance of a service goes down or a replica goes down, the Docker runtime automatically brings that particular instance of the service for you. So you don't have to really bounce the container by yourself. Now that concept is a bit different from the application health check. Now there are capabilities to do that in Docker as well, which we'll talk later. But the point being, if a container goes down, the container may be healthy, but the application inside the container may not be healthy. So those are 2 separate things. So you are responsible for the application health. There are primitives in Docker that enable that, but this will make sure that the number of containers are running, which is important. Some other primitives that are built into Docker itself is, for example, you have a 6-node cluster running here. There is a node that fails. It happens all the time. If a node fails, because it's a declarative state, there is always a health check that is running on the cluster that you said 3 replicas should be running, and at this point, I'm only running 2 replicas. A new container is automatically spawned on the rest of the cluster. So the reconciliation of the desired versus actual automatically happens for you. Another example, well, the cluster stays exactly as is, but the container dies. Independent of how the application is behaving on it, let's say the container dies. If the container dies, again, the same thing. Desired is not equal to actual. Let's reconcile, and it fires up a new container somewhere in the cluster. Now, there are ways and means by which you can influence the scheduler algorithm. We'll get to that a little bit later in the presentation. Okay, I fired up my service. It's a 3-instance service. I want to scale the service. So remember I talked about the Docker CLI being structured. So now instead of saying Docker service create, I'm saying Docker service scale. I just give the service name, and I give the number of replicas, and it just magically fires up the containers for you across your cluster. Now, the concept that we have talked about so far is replicated service, where you're saying, OK, I want to run so many replicas of the container, and it'll automatically do that for you. Now, you could also do, for example, a global service. Think of it as a singleton instance of a service, 1 instance of a service on each node of the cluster. So in this case, you're saying Docker service create, and you specify the mode as global. The moment you specify the mode as global and the image name, it's going to download that image on each of the nodes, and it's going to fire up the service, and it'll make sure only a single instance of the service is running on each node. So Prometheus, for example, is a very commonly used logging service. So you can say, well, now the Prometheus endpoint is baked into Docker itself, but earlier you could fire up a Prometheus endpoint very easily across your cluster very easily, and then you can aggregate the data from that into an elk stack or something like that. So that would be a sort of a typical common use case. Any questions on Docker concepts so far? We'll get to that. We'll talk about service discovery, load balancing part of it. That is right. Yeah, that is right. So the question is that when you're looking at this cluster, is your entire application deployed over here? So I mean, depending upon what level you want to start from, essentially you're looking at probably a bunch of EC2 instances running. On top of that, you have your Docker setup, and on top of that, you're running your containers, and those containers could be stateful or stateless. Your elk stack, you name it, your NoSQL database, whatever you want to run, they're all running over there. And when we talk about the databases particularly, then you have your volumes attached to it because that's where your data is being stored. Then you're talking about your Docker so the whole thing runs over here. Yeah, but that's exactly how you need to think about when building your application essentially. Okay, let's take a look at it. Now, with Docker as the base layer, we understand how the Docker Swarm cluster is created, how we can have service in a declarative way, how the service reconciliation happens. Let's take a look at Kubernetes side of it. Now, Kubernetes is an open source scheduler framework. It was originally created by Google, donated to CNCF now, which is Cloud Native Computing Foundation, and that's where it's being maintained. Still heavily inputted by Google, but a lot of other individual contributors as well. So in that sense, that's pretty cool. Even though Kubernetes claims that they are container agnostic, but most of their work is relevant to Docker in that sense, as Docker as an image and the runtime format. They talk about, we run with Rocket and other container formats and OCI compliant formats, but that's still, the work is there. Anybody know anybody running Rocket in production? Exactly. I've been giving this talk for over 2 years now. Other than the core OS guys, I have not heard anybody running Rocket in production. So as much as Kubernetes claims that they are compliant with, they are container agnostic, but it's all about running it on, with a Docker container format and a Docker image format. It's good to have Kubernetes because it kind of allows you that container agnosticism when it's available, but that's the lead today. All right, now, so think of Docker as the basic basis you need for running your application on Kubernetes. Kubernetes is an orchestration framework or a scheduler framework built on top of Docker in that sense. Now, Docker already has Swarm mode baked in. Now, for some reason, if you don't like it or you need a little bit more variety of it, you can look at Kubernetes. In Kubernetes, it has a bit of a steep learning curve. One thing that I love about Docker Swarm mode is how it's baked in, it's available for me. So if I want to get started, I just say, Docker Swarm in it, and I'm ready to roll. With Kubernetes, it's a different set of terminology that you need to learn. And that was sort of the hardest part for me to put my head around it. Now, in this case, I'm looking at pod. Pod is essentially a collocated group of containers that share an IP, namespace, and a volume. And what I mean by that is, think of it, think of your Valve. I'm not saying really your database and your application server should live in the same pod. No, that's not the case. What I mean by that is, let's say you have your application server and a sidecar container for, say, extracting logs from it and putting it somewhere else. Those things, they can live together. And the idea is by sharing the storage volume and IP is essentially, these containers can then talk to each other using HTTP localhost because they're in the same pod. So essentially, the unit, the basic unit where we can play around with in Kubernetes is a pod. Just the way we have service, in Docker Swarm, here is another abstraction layer called as replica set. In replica set, you can say, I want to run X number of instances for a particular pod. And the way you define that in Kubernetes is using a configuration file. In the configuration file, you specify the complete pod template specification, the number of replicas, all the metadata, et cetera. And then you say, go run this replica set. And it'll run the replica set for you. And there used to be a concept called as replication controller. in the earlier versions of Kubernetes, but replica set is where they're evolving towards now. Now, just like containers, pods are ephemeral, and if a pod dies, the pod will come up on a different host, maybe assign a different IP address. So that IP address is something you cannot rely upon. So very similar to what Docker already has. So essentially, they have this concept of a service. Service is a logical name, which also acts as a load balancer for those different pods. And essentially, the way these are tied up together is using labels. So a pod comes up, pod has a certain labels. Those labels are stored in a etcd registry, which is by default comes with Kubernetes. It's a distributed watchable registry. So a pod comes up, it stores those labels in a etcd registry. Service is a concept of Kubernetes, which is looking for those labels in the registry. So imagine this. You have a bunch of pods wrapped in a replica set. So you can now dynamically scale the replica set up and down. And then service is looking for the labels coming from the pod. So that bit of an abstraction is there. It's a little bit of an extensibility layer, but it seems to work once you understand the basic concepts. Now, those are sort of the developer core concepts from Kubernetes side of it. If I look at it from the ops side of it, of course, there's a concept of a node. It used to be called as a minion, actually, in earlier versions of Kubernetes, and that minion terminology is still prominent if you use a kubectl CLI. But essentially, it's a machine or a VM in the cluster. It doesn't matter, whether you're running on-premise, in the cloud, whatever. But they have this concept of a master, which is sort of your central control plane. Just like a Docker manager, they have this terminology called as master. It provides a unified view of the cluster. It has several components. So for example, one of the components is the API server. Now, if you contrast Docker and Kubernetes, with Docker, you make a command, say Docker run this container or run this image as a container. Then behind the scenes, under the wire, what goes is a REST API request. And so there's an API server listening on the Docker host, essentially. So very similar concept here. There is an API server listening over here. You're using the kubectl, which is the Kubernetes CLI, to make a request to the Kubernetes server. And then that API server is the one that's listening for those requests and does the thing for you. Controller manager is something for things like replica set, where it says, okay, how many instances of a particular pod you want to create. Then there is a concept of scheduler, which says, okay, I have a scheduler algorithm, and I need to take a look at it, which container to be scheduled on which host, and stuff like that. Now, by default, in Kubernetes, the master cannot run any containers. So you have the concept of a worker, which is basically nothing but a VM or a host which is running sort of the Docker host for you automatically. And it also has this concept of a node agent, essentially, which is what the manager is talking to, saying, okay, I want to deploy a container. Let me talk to the node agent. And the node agent essentially is called as a kubelet. That's sort of the Kubernetes terminology. And all of your containers are running on the host using kubelet. Depending upon the operating system that you are running, essentially, on your workers, the containers themselves are monitored by systemd, monit, and stuff like that. So there is a very close integration with that underlying operating system primitives as well. So if I were to look at sort of the broader picture of how my Kubernetes architecture would look like, I do have a manager or a master. The kubectl API is the kubectl CLI is essentially what I'm saying is, go run these containers. And to the kubectl CLI, you will specify a configuration file where all of your Kubernetes primitives are specified on how it needs to look like. That goes to the API server. API server then talks to the controller, the manager, etcd, whatever, you're creating service. It looks at all of that information. And then it says, okay, I got a couple of workers over here. And in those couple of workers, I will talk to the kubelets, and I will deploy the pods and the replica set. And whatever needs to be done, I'll do the right thing over there. The kubelet will then actually kind of deploy it across. And there's a proxy service running on each of the worker as well. So essentially, if you look at it, your request comes in from the client, which is sort of the internet bubble or internet diamond on the top. It goes to a load balancer, which is typically well integrated with your proxy service running on each node itself. So request comes from internet from the client to the load balancer, which then goes to the proxy, and when it says, okay, I know which container can serve the request. There are different ways by which the load balancing could happen, and there are different algorithms that are available, but I could not find out a way by which you can actually influence that algorithm, though, and that's sort of the default algorithm. So essentially, if you do want to influence it, the way I've figured it out is you write your own little bit of a load balancer algorithm to play with it. So if I look in this diagram, essentially, this is sort of what my Kubernetes cluster look like. These are my Kubernetes core components. But the kubectl is what you are interacting with, and internet and load balancer on the far right is where you are interacting with it from your side of it. Any questions on Kubernetes concepts so far?
I guess it's a comparison, maybe you're going to get to that, but so with Kubernetes, you have the IP address or the alias, right? That is essentially an alias, an IP alias for the worker or that host machine. Does Docker Swarm do anything comparable to that, or? And I guess that gets into like being able to bind, the same port to the same service.
Yeah, we'll talk about how the service binding occurs actually. Now. Nowhere you access the service by the IP address. You expose the service by a logical name, and that's where you access it, whether it's Docker Swarm or Kubernetes, both ways, in that sense. In the Kubernetes? No, I don't think so. Because proxy is the layer which basically figures out which container is where you're going to. See, end of the day, you have a service object. Service object is the one that is your logical name, which is then having a replica set, which is then kind of where you are scaling your parts in and out. So you are making a request from a Java application. This is what we're going to cover next. You're making an application request from a Java application to a database service. So service then kind of deals with proxy to kind of go it down directly there. Now, you may think, oh, it's doing an additional hop, but essentially it's just a bunch of etcd labels. So it's not really a network hop per se. Correct, and the etcd infrastructure is pretty scalable in that sense. All right, so the next concept that I want to talk about essentially is how does service discovery and load balancing works in both of these frameworks. And my simple sample that I wanted to get working here is I have a simple Java application that I want to talk to a database. How does service discovery work? How does load balancing work in all of those aspects? Okay. So now, typically the way you deploy a multi-container application, I mean, if you think about it, Java application server and a database are two different containers. So now I'm deploying a multi-container application in my cluster. So the way you deploy a multi-container application is you define them using Docker Compose. Now, Docker Compose is nothing but a YAML file, which is where you define what your application definition is going to look like. By default, the file name is also dockercompose.yaml. And there are other means by which you can have multiple Docker Compose files. You can override the definition files. And those are particularly very useful for reducing the impedance mismatch. So for example, you could have a Docker Compose.yaml, and then you can have Docker Compose prod.yaml. Depending upon which files you are invoking the Docker Compose with, it could be just a dev environment with Docker Compose, and then you can override the services, say the port numbers, say their privileges, the access keys, and passwords for the prod environment, and then you can invoke it with that particular combination. I won't dig into the details for Docker Compose, but typically that's where we see customers using Docker Compose for cutting down the impedance mismatch between dev, prod, CI, and also cater to different environment variables, how they can use environment variables to cater to different environments based upon their needs. How do I do service discovery with Docker? Well, here is a simple Docker Compose YAML file, and if I walk you through this, this is the version 3, so you need to realize this is version 3. There has been 1, 2, 2.1, and I believe 2.2 as well. I think 2.1 is the one that I remember. But this is the latest version of the Docker Compose file here. In this Docker Compose file, if you look at line 2, I'm essentially defining services. Line 3 and line 10 is where my two services are defined. And I'm saying the names are up to me. I'm saying DB is the name of the database service, and web is the name of the web service. Now, in the DB service, line 4, I'm saying That's my image that I want to use, okay? Now this image is my custom image. All I've done is I've taken a Couchbase database and I've pre-configured it using its REST API, and I've also populated a simple bucket in here which has a bunch of JSON documents, about 30,000 documents in there. So all of that image is baked in for me using that tag. So Arun Gupta / Couchbase : travel. If I run that image, I know once that image is ready, or once the container is ready, my Couchbase server is ready to receive the request with that bucket pre-populated. So that's kind of cool. Now, then I'm exposing certain ports. Those are my admin ports, my query ports, which my application needs in order to talk to them. And then in the line 10 through 16 is where I have a simple application. Line 11 particularly says that's my image. And in there, the image is Arun Gupta / Wildfly Couchbase Java EE, again, : travel tag. That tag, the image name is completely up to me. So that's sort of the rhythm that you will have to figure out. That's sort of the pattern. You'll have to figure out what works in your organization. Now, in this case, what I'm doing is I have built a simple Java EE application, which is deployed in Wildfly application server. And that Java EE application is looking for an environment variable by the name Couchbase _URI. And essentially, that's the only environment variable it's looking for, because that application reads that environment variable, and that application uses Couchbase Java SDK to talk to the Couchbase database wherever it's running. Because once I know the host, I can default to the port, and I can just connect with it directly. And that's good enough for me. And guess where that environment variable is coming from? That's coming from line 12 and 13. There I'm saying Couchbase URI. And the cool part here is I'm just using the service name. I don't care where the service is defined. So that makes it really seamless for me. Because the service today, may be running 1 container. Tomorrow, I might have scaled the service to 4 containers. And the service will automatically do the load balancing for me. And from the application perspective, application developer perspective, I'm just caring about Couchbase URI variable. And of course, I'm exposing my ports for the Wildfly service as well. So literally, if you check out this Docker Compose file, copy paste the content of this Docker Compose file, and you say Docker stack deploy, because I'm deploying this as a Docker stack essentially, and I can say, here is my Docker Compose file, and here is a stack name. If you take this, if you have a brand new machine, so what will happen behind the scene? It'll download the Arun Gupta Couchbase travel image. It'll download the image for Wildfly Couchbase Java EE, and then it'll run the container. And one of the things that is missing over here is, for example, I could also specify the dependencies on containers. That, start the DB container before the web container. Something that is very important to understand over there is it only says the order in which the container needs to be started. Now, a database container typically takes a longer time to start before it's ready to accept connection requests. So that application level health check, again, you have to bake it into your application. So in my Java EE application, essentially, I know that I've been able to resolve that service name, which is good. But then I will keep pinging the database service. Hey, are you ready? Are you ready? And then once I know it's ready, then I will actually make a query. So I think that differentiation is important. Docker Compose, what it provides you is the ability to say, OK, start the containers in this order, but the application ordering is completely up to you. So essentially, the way I see this is, well, this is not a complete slide, but essentially, I have a big stack. In the stack, I have a service, in this case, a DB service and a web service. And a service could have multiple tasks. And each task is essentially a container. So that's sort of my encapsulation of it. I need to make it a little bit more colorful, add some more images to it. But that's sort of my encapsulation to what this means, like, on how you run a typical application. Now, whether I have a web service or a DB service or a caching service, those are all essentially encapsulated as services where you're talking to each other like that. How does load balancing work here? So now I'm running a 5-node cluster here. And in the 5-node cluster, I'm only running 3 instances of Wildfly application server. But what I've done is I've exposed port 8080 on the host to the port 8080 on the container. Now, your load balancers are typically not container aware. They are indeed host aware, though. So the beauty is if you make a request, now, I mean, essentially what you do is in your load balancer, you configure that, hey, here is my worker.properties, or here is my Nginx configuration file, and here are the 5 nodes that are actually where my services might be running. So you specify those 5 worker nodes in your Nginx configuration file. The request comes in from the client. It goes to the load balancer, whatever your load balancer is. Then it could go to, I mean, depending upon the algorithm, it could go to a node which was not, which is sort of fits into the algorithm. And if a container is not running on that node, it's just a simple network hop. It uses IPVS. It's a very efficient network call in that sense. It just hops onto the node where the container is actually running. So from your load balancer perspective, your configuration file stays exactly the same. But if your service is scaling up and down, and if your containers are getting rescheduled all over the place, it wouldn't really matter from your perspective, because the request goes to an empty node where the container is not running. It automatically popped over to the node where the container is running. Let's take a look at the similar concept in Kubernetes as well now. So as we talked about it in Kubernetes, we are using service as a concept which abstract a set of pods, which are using a certain labels. You just uses simple TCP, UDP load balancing. And essentially, it creates those environment variables. There are a couple of ways by which you can access the service. And essentially, very much like Docker, what it gives you is a stable endpoint for the pods to reference. That, okay, I'm a web application pod. I need to talk to a Couchbase service or a database service. Give me a logical name. The configuration file here is a bit daunting, but let me walk you through this. Essentially, what I've done is, this is one configuration file, and I've broken it down into 3 pieces. The first piece on the left is what my service definition is. The one in the middle is my replica set, and then one in the far right is also a replica set, okay? Now, typically, you would never run a pod by itself, because if a pod dies, it dies. I mean, the pod may have a restart capability, but it may not. So typically what you do is you always wrap it in a replica set, even if you want to run a single replica, which is okay. So the one on the far right is basically my application pod, which is my Wildfly Java EE pod. Then on the 2 left parts of the configuration file, if you look at the middle one particularly, that's where my Arun Gupta Couchbase Java EE, Arun Gupta / Couchbase travel image is running. That's my Couchbase image. Now the key part here is, when I'm firing up my Couchbase pod, on line 27, I'm specifying this pod has these labels attached to it. These labels are completely up to me. Labels are nothing but a name-value key pair. So I'm just saying, here is a name, here is a value, and that's what goes into, as part of the metadata, into etcd. And then in the service, which is on the left side, I'm saying, oh, this is my selector. And in the selector, I specify similar name pods, or the name-value key pairs. So essentially, now I can automatically scale my replica set up and down, and the service will keep looking for those name pods or the name value key pairs, and accordingly make it as part of the service. And then last but not the least, the service has a name, and that is the logical name that I'm actually using into my Couchbase URI. So see how a same application is just relying upon Couchbase URI as an environment variable, and then be able to communicate it, whether it's in Docker or it's in Kubernetes. And I have a similar sample working on DCOS as well. So one of the talks that I'm giving next week in Germany is how to run service discovery in 4 different container orchestration platforms. So if you are looking at ECS as an option, which is Amazon Elastic Container Service, service discovery is a bit tricky over there. So I've been working with those folks to kind of dumb it down and simplify it, though. So essentially, if I'm running a single node Kubernetes cluster, then I have a Wildfly pod or a replica set running that will be talking to a Couchbase service, which then guides it to a Couchbase pod. Or I could have a front-end service and a back-end service, and then they can communicate with each other. Well, this is the actual pod. This is the actual pod for Couchbase. Remember, we need a Couchbase replica set, we need a Wildfly replica set, and we need a Couchbase service. So first is the service, second is the pod in a replica set, and third is a Wildfly pod in a replica set. Well, I mean, there is no Wildfly service. It's a Wildfly replica set, if you see in the far right. I don't need a Wildfly service. Well, I can go here. I'm just showing you what's possible, essentially. If you have a replica set, depending upon the labels, you could easily create a front-end service. Now, think about this. If you have a web server. Now, I know Wildfly 10 particularly has the web server capability itself. Now, if you don't want to use that, let's say you want to front-end it with Nginx, then the Nginx could say, I just talk to this front-end service, for example. So lots of different ways. I'm just showing you the possibilities that are available. Correct. Correct. And, well, if you don't want to reference it somewhere else, then it's probably lying somewhere where nobody knows about it. All right. Switch gears. Let's talk a little bit about persistent containers. So I'm going to show you some of the approaches that are possible both in Docker and in Kubernetes in terms of persistent containers. This is where we're running stateful containers. So the stateless containers are like diapers. You shit in them, you throw them, you bring a new one on. That's OK. But you can't do that with stateful containers. There's a lot of shit. There's a lot of data in that shit. So you want to hold on to that. So what you do is you scoop it out, you put it somewhere else, and then you bring a new diaper in. So let's talk about persistent containers. Okay? The 4 different ways that I've seen persistent containers working in Docker. Well, Docker has this concept of volume, essentially. If you run a container by default, and like you just run Arun Gupta /Couchbase : travel. So what it's going to do is it's going to bring up the container for you. It's going to give you a default volume, which is in the container itself. But when the container dies, the data dies. You have no access to the data at all. Well, that's OK for early prototype phase. But as you go into advanced prototype, more dev sharing kind of a phase, that doesn't work. So let's talk a little bit about it. What are the different phases? What are the different ways you can do persistent containers in Docker? So first one is the implicit per container space. That's the default sandbox that is available to everybody. The second thing that is available to you is where you can say Docker volume create. Remember we talked about CLI restructuring? That is pretty handy. So now you have a Docker volume command by which you can create a Docker volume, and you can associate a name to it. That name can be then repurposed by others. The third approach is where you can say, I want a directory on a host. So for example, the way I run Couchbase is I would typically say, I know when Couchbase writes data, this is to opt var Couchbase. That's where all my data is stored. So what I could do is I could map that opt var Couchbase in the container to ~/Couchbase. So then if my container dies, and if I can bring up the same container, do the same volume mapping, it will still have access to the same data. But again, the problem over here is tied to a host. OK for dev and early prototype. But what we really need is a storage where the containers are scheduled left and right across the cluster, whichever host it goes to. So you need a multi-host storage solution. Okay? So those are the 4 different scenarios that we're going to look at it. Now, by default, the location for what these volumes are, this is for implicit per container and explicit per container. They are both on var lib docker volumes directory. That is on the host. So for example, if I'm running excuse me, if I'm running on Docker for Mac, then I have a means by which I can ns enter into the Docker for Mac VM, and that's where I could see var lib docker volumes. But that's on the host, not on not on my Mac machine. In the Mac VM, or the X-Hive VM that's essentially running. Per host, of course, is mounted within the container, but the directory is living in my ~/Couchbase. And then for multi-host, there are solutions like Ceph, GlusterFS, NFS. So you can mount it in a network storage. And if a container dies, if it comes up on a different host, you still have access to that volume, whichever host is coming from. The important part over there is you need to figure out some naming mechanism, some schemes by which you can figure out which container is mapping to which particular volume. So there is more work involved in terms of planning for that. And we'll talk about how that can be simplified. So what happens if a container crash? Well, if it's an implicit per container volume, as I said, if a container crash, the volume is gone. It's not accessible to you. I mean, it still lives on the host, but that's not something you have access to. I mean, I can hack it out. I can log into the NS enter into the Docker for Mac VM. I can figure out, oh, what was my volume ID and stuff like that, but pretty meaningless. In explicit per container case, the directory is still on the host, but again, not available to you. On per host, where I'm doing my Docker volume mapping, say / tilde Couchbase to opt var Couchbase, that directory is available to me because it's on my host, and it's okay. I don't care about the container because the data is what is critical to me. And then in multi-host, of course, is living somewhere else, so that directory is always accessible to me, the data, more importantly. What happens if a host crashes? Well, if my MacBook crashes, no matter what, I don't have access to the directory, the data at all. Explicit per container doesn't matter. I have an explicit name, but the volume is still living on the X-Hive VM, which is sitting on my Mac, so I've lost that. Tilde / Couchbase, now if my host crashes, I don't have access to that directory. And again, if I go to the multi-host, I do have access to the directory. If this MacBook crashes, I just bring a new MacBook, and I know the data is sitting on a network storage. And in terms of sharing, the implicit per container is certainly cannot be shared because that is implicit per container. It's a sandbox for that container. If a container dies, everything is gone. The explicit per container one, you have an explicit name to the volume, and that can be shared among different containers. Per host, yes, can be shared, but only on the host. And then the fun thing is where you're looking at really, hey, this is my cluster wide storage and how it can share. So these are sort of the 4 typical use cases I've seen of running persistent containers and what are the different storage strategies that people have applied. Now, are there ways, means by which this can be simplified? Yes, let's take a look at that. Docker comes with an architecture of Docker volume plugin, okay? And it kind of follows the batteries included but replaceable story that Docker has been telling all along. And what that means is, essentially, there is a default driver that is already available in Docker. So the implicit sandbox that we talk about, the explicit volume that we talked about, that is sort of the default battery included with Docker. You want more power, take that battery out, put a new battery in, and let's turbocharge it. So that's sort of the idea over there. So essentially what it is, is you can have plugins that would enable the containers to be integrated with external storage systems. And what are some of the examples? Well, EBS, GCE, persistent disks. You pick a name. There are a variety of storage systems. MinIO, Dell EMC, X-Ray. You pick a variety of storage systems, and there are plugins available to integrate with those. So how does the Docker volume plugin architecture looks like? Well, we are familiar with the Docker client and the Docker host. We are happy with that. Plugin client, is an additional library that is available, additional CLI rather, that is available to you. But important to that, there is a plugin daemon that you need to run. And I'll show you with an example. But a plugin daemon essentially gives you access to a variety of storage backends. That plugin backend knows how do I connect to an NFS or a Ceph or a Gluster FS or a EBS or a GCE persistent disk. How do I store data from there? How do I get data from there? How do I resolve conflicts from there? So that's sort of the role for the plugin daemon. And then there is an additional CLI available to you, which will allow you to manage that daemon if you want to. And as I show up here on Docker host, for example, we have this default local driver built in. That's sort of the batteries included principle. And by using the plugin architecture, that's what the replaceable architecture is. So the one that I'm going to talk about is Portworx. Now, Portworx offers you, allows you to build stateful containers very easily. And essentially, what you do is, the sample that I'm going to show you here is, I'm going to run, Portworx comes in 2 flavors. There's an open source flavor, which is pxdev, and there's an enterprise flavor, which provides a lot more capabilities over there. But essentially, what you do is you fire up a pxdev container in addition to your stateful container, and that pxdev container is then responsible for mapping your containers to the volumes where they are hosted, okay? So, and the Portworx client essentially allows you to take snapshots and stuff like that for your data volumes. In this case, what I played with is, this is one of our customers who's using it. They are using the pxdev container to map it to Amazon EBS. And essentially what happens is, now if my container dies, it can come up on a multi-node cluster. If my container dies, it comes up on a different node. The pxdev container is monitoring that and it says, oh, I know this container dies here. It came up on a different node, and I know the mapping that the way it needs to be done. Because the volume is sitting on EBS, I can resurrect that mapping for that particular container. Similar concept exists in Kubernetes as well. So Kubernetes also has the concept of volumes. Now, one of the complaints that the Kubernetes team has made is that, okay, the directory, the Docker volume lifecycle is not well defined. But that is up like beyond, that was in Docker 1.7 essentially. So I want to see that comment going away, given the fact that we are in 1.13 now. But essentially, it's nothing but a directory that is accessible to the pod, and they have a different kinds of Kubernetes volumes. You can have a host path and a fest path. So very similar to what Docker already offers. So the two frameworks are very comparable in that sense. How does a Kubernetes persistent volume work? Well, Kubernetes volume is okay, but that, if a pod is, a container could be restarted within a pod, but what if a pod dies itself? Then the volume is not of much sense to you. That's where Kubernetes persistent volume kicks in. The Kubernetes persistent volume is a multi-step process, essentially. So what you do is you create a network storage first, or you provision a network storage. You could have like a 160 gigabyte SSD on EBS running. And then that's sort of one storage that you've done. Then you say, OK, I want to get a claim of that storage. Out of that 160 gigabyte block, I only want to get a 10 gigabyte block. So you can request a PVC, which they call as a persistent volume claim. And once you get a claim, then in your configuration file, you can use that claim. That, OK, this is the claim that I've occupied, and this is the claim that I'm going to connect to. And then you can start using that volume, how you want to do this. And then after that, if your pods go up and down, that mapping is automatically done for you. And just the way Portworx has integration with Docker, they also have integration with Kubernetes. As a matter of fact, we're working with a very, very big SI and a customer. It's a joint use case where they want to use Kubernetes plus Portworx together with Couchbase to build that scalable infrastructure. So how does it work in Kubernetes? And I see if this is sort of the multi-node architecture for me. So one master, two worker. I have a Couchbase Docker container running over there, running as a replication controller or replica set. I could expose it as a publicly accessible service in the purple box over there. Now, by default, if I run the pod, essentially, my storage is on the host, because that's just following the Kubernetes volumes model. What we want to do is we want to extract the storage, move it to EBS, and we want it to live there, so that if my pod actually gets rescheduled, it is automatically mapped over there. So just the way we talked about it, for example, if my pod is now rescheduled to worker 2 in this case, just because there's a Portworx container running on each pod or in each host, it'll automatically do the mapping from the container to where the volume is living. So, earlier there used to be Flocker or Cluster HQ. They were used to offer it, but they shut down their business, I think, sometime in November last year. So this is sort of the most credible offering that I've seen in terms of volume mapping, essentially. There are other tools as well, but I know I've played with Portworx for both Docker and Kubernetes. Let's talk a little bit about the development offerings here. We're about 5 minutes away. So now Docker recently changed for good, for simplified version on how they deliver it to the community. Earlier, there were confusing versions. It was hard to figure out what is experimental, what is GA, and stuff like that. But I think the new model is a lot cleaner and easier for me to understand and explain as well. So essentially, Docker is now available in 2 flavors. There is Docker Community Edition and Docker Enterprise Edition. Okay? Docker Enterprise Edition is the one that is released quarterly for every version and supported for a year. That's sort of the commercial version of Docker. And on the top, what you see is Docker CE. Docker CE comes in 2 flavors, Edge or Stable. Docker Stable, as you see, is, this is March. 9 more days in March. So hopefully we'll see a stable release every 3 months, and that'll be labeled by year and month. So for example, we'll see 2017 March release for Docker CE Stable. And then there is the Edge release. Hey, I want to be on the bleeding edge of Docker all the time. By the way, Docker for Mac, the one that I use, they automatically push updates to me. So if I want to be on the bleeding edge, then I'm going to go to docker.com/get-docker, and then I download the edge build from there, and every month they will push the releases to me. So there's a bit of a predictability and a cadence over there, which tells me that, okay, something is coming my way. So if you want to play with Docker, then CE is the version that I play with all the time. EE is their commercial supported version. If you want to play with Kubernetes, the real option for you on a single node cluster is Minikube. Minikube is really compelling. Just like Docker for Mac is written as a X-Hive VM on top of a hypervisor framework on a Mac, Minikube is similar, very similar to that. The multi-node cluster story is a little bit crooked, in my opinion, for Kubernetes. They used to have this script called as kube up. And in the kube up, first of all, there is no way to specify the number of masters. You can only have one master to spin it up on AWS. Now, they've introduced this tool called as COPS, Kubernetes Ops. So just the way there is kubectl for doing developer stuff, you can use COPS for creating those clusters on Amazon. The usage, in my opinion, of COPS, and look at my blog, and I've blogged about this topic in detail on how do you set up a multi-node Kubernetes cluster using COPS. The CLI is a bit cryptic. In a very classical Google sense, it requires a rocket scientist to fire up a command for COPS. They need to dumb it down further. So I've been harassing those folks on the Slack channel. But there are other options as well. So there is a CloudFormation template, I believe, by Hept.io. These are the guys who were initially founders of Kubernetes, initial product managers. They have created a new company called as Hept.io. They have a CloudFormation template. So there are a few things moving in the right direction. But I think the story is a little bit crooked in terms of single node cluster or multi-node cluster, which is, I think, a lot more seamless in case of Docker. Let's take a look at rolling updates. Okay, now, what is rolling update? That's a necessity of life. I have a version 1 of my Wildfly application running, and all I want to do is I want to upgrade the version one by one. I don't want to just say, bam, just kill everybody and bring everybody out. So the command for that is, again, Docker service update. I'm updating the web service, and I'm saying use the image, which is wildfly::tag2. So that's my tag, essentially. And then I'm saying update parallelism. What that means is update 2 at a time. And then I'm saying after you update 2 containers, wait for 10 seconds. Let the cluster settle down, and then update the next 2. So, I mean, there are some options available to you. You can play around with it, see what works for you, what works for your setup, how much settle down time you need, how many parallel updates you want to make. So that's sort of the command that they recommend, essentially. There's a similar concept in Kubernetes as well, where you can do a rolling update. Now, a rolling update in Kubernetes would really mean is rolling update a replica set or a replication controller, because essentially that's where your service is. So remember, service, replica set, and the pods. And what you want to do is update the pods in the replica set. So here, for example, I have web app-rc, which is my replication controller. All of those pods are putting labels in the etcd registry. So the way Kubernetes does it is, it says, OK, you give me the command. Once you give me the command, then I'm going to fire up another replication controller with version 2. Now, at that moment, of course, you have 6 containers running with very identical, like 3 with version 1, 3 with version 2, but they all have the same labels. So your application service essentially would start distributing requests to those 6 different pods in 2 different replication controllers. But essentially, over a period of time, like literally in a few seconds, that pods, or once all the pods on the lower replication controller are spun up, and the ones on the top are gone, and eventually that replication controller is gone, and this replication controller is renamed as well. So, I mean, I'm just showing you the guts of the technology because that's what I like to do. But this is what happens behind the scene. The commands, are again explained very well on my blog or on the GitHub repo, actually. They're explained over there. And by the way, all of these slides are available on my GitHub repo. So go to Arun-Gupta, Docker. Well, this is this particular one. I think this is Docker-Java. So all the slides are available over there. I'll show you a pointer to that. Talk pretty much about the last thing here, monitoring Docker. Now, several APIs are baked into Docker itself for monitoring containers. The basic API, which is the Docker CLI API, you can say Docker container stats. It just sends you stats every second it refreshes the screen automatically. There's a Docker remote API, and I wrote a blog on that recently on what are my options and how do I monitor Docker. So take a look at Docker remote API. It gives you a lot more details about monitoring data for a particular container. Then if you're running a multi-node cluster, if a container goes down, container comes up, service scales, node goes down, whatever happens, you can use a Docker System Events API, which gives you all those eventing notifications. Then you can build your frameworks on top of that. A couple of more options that I've seen people using. In Docker 1.13 Edge release, they have introduced the inbuilt Prometheus endpoint, so you can start collecting logs from that. And C-Advisor is something that I've seen people use it pretty popularly. But the problem with C-Advisor is it only shows you data for 60 seconds. So you really have to start backending it with InfluxDB and then put a Grafana dashboard in front of it. This is an example of a Prometheus endpoint on what kind of information that it shows over there. And then in monitoring Kubernetes, again, there is a baked-in solution available for you automatically. Essentially, you have a C-Advisor container running on each of the node by default. This is automatically baked into Kubernetes. What you do is you fire up a heapster, well, not you fire, this heapster container is automatically, heapster pod is automatically running for you. It's got a bunch of containers in there. And there is an InfluxDB plus Grafana dashboard available for you. This is all available to you in a standard Kubernetes cluster without any work, essentially. And then heapster is the one that is collecting the cluster information, is aggregating it, storing it into InfluxDB, front-ending with the Grafana dashboard. And the way heapster collects that information is by talking to kubelet. These are some of the Grafana dashboards that are available to you out of the box. And again, I blogged about this, so if you Google on this using my name, you will find how to create these fancy dashboards very easily. There are, of course, commercial tools available: Sysdig, New Relic, Weaveworks, Datadog. They all offer Docker plus Kubernetes monitoring. I have an article coming up on Sysdig soon, so stay tuned for that. Well, that's where my slides are. So yeah, docker.io, kubernetes.io, all the details are over there. And if you like the talk, go to my DevOps, rate the app and the talk.